all of you participants who have joined us in this lecture series today with us online as well as offline. Today we are going to have our second lecture. I'm sorry, 22nd lecture in this monthly scientific interactive series that will be delivered by Professor Aditya Kumar Patraji, Associate Professor, Department of Mining Engineering from IIT Kharagpur. He will be discussing on carbon capture, utilization, and storage, present scenario, and future perspectives in Indian context. Uh, to start with, I would like to request the member secretary of this board, Sri S. Chandrasekhar ji, to present the welcome address for today. Sir.
Respected Honorable Chairman, Bihar State Pollution Control Board, our esteemed speaker of today's lecture, Professor Aditya Kumar Patra, sir, Associate Professor, Department of Mining Engineering, Indian Institute of Technology, Kharagpur. My senior colleagues who have joined physically here, all my junior colleagues, and all the participants who have joined through virtual mode. I welcome you, all of you, for this monthly lecture. So, for your information, Bihar State Pollution Control Board has been organizing monthly lectures since more than 1 year now. This is the 22nd lecture, sir, in the series. The objective of having to have this lecture is to create awareness and to elucidate interest among the academia, researchers, school students, college students, and the general public. So, so far we have covered various topics related to environment, and also we have covered few of the topics which are related to purely a deep dive into the research field. And so far we have got a good feedback from the participants, sir. So, in line with the this lecture series, we have decided to have a speech, a lecture on the topic carbon capture and related issues. So, I am thankful to you for accepting our request for delivering this lecture, sir. So, with these few words, I again welcome you on behalf of our chairman, Bihar State Pollution Control Board, for delivering this today's lecture, that is carbon capture, utilization, and storage, present scenario, and future perspectives in Indian context. Sir, over to Dr. Naveen, please.
Thank you, sir. May I request Chairman, sir, to please deliver his remarks on this important topic that we are going to discuss today.
Good afternoon, everybody. Professor Patra and colleagues. In fact, this lecture has stemmed from the paper by Professor Patra and other colleagues, and it has attracted our attention because our total attention about the climate change and other features are focused on only one aspect, that is the control of emission. And control of emission, like a country like India, we have several problems to control to a limit. The another mechanism which has never thought of in our discussion, that is the carbon capture mechanism. The green plants, as we know, that they can capture the carbon and prepare the food. But for the mechanical means and the engineering options, we are not aware. So for the first time, that paper has explored in detail the various aspects of the carbon capture mechanism. So we thought that it is better to hear from Professor Patra about the various options available and the cost of energy which may be available for this capturing mechanism. This lecture, I would request Dr. Patra to limit the lecture, especially on the mechanism which are very familiar to us, but we don't know the engineering aspect of these capture mechanism. So it is better to focus on this aspect because all the present here in the audience are have scientific background, so they can understand it. Thank you very much.
Thank you, sir. Uh, I feel myself privileged to introduce you to the eminent speaker for today's lecture. As you know, is Professor Aditya Kumar Patra, working as an associate professor at IIT Kharagpur. It is a real privilege for us to have Dr. Patra with us. He is a PhD in atmospheric sciences from Center for Environment Policy from Imperial College of London, UK, and also an MBA in operations management, quite a diverse field from Indira Gandhi National Open University, New Delhi. Uh, Professor Patra has a wide experience in these sciences, and he is an executive fellow from the School of Minerals and Energy Resources Engineering, University of New South Wales, Sydney. Commonwealth Academic Fellow, Department of Earth Sciences from Imperial College London, and many other professional uh, attachments he has. So many fellowship and scholarships are attached with him, and he has his research interest in fine and ultrafine airborne particulate matter in urban environment, its measurements and modeling. So that is a real field that is of very much interest of the state pollution control boards, including us. He has worked in indoor air pollution, dispersion of respirable particulates, pollutant dispersion in deep open cast mines. So he has a very wide experience in this, and we are really very happy that he is going to dwell upon the about carbon capture, utilization, and storage, and that is very much important and of topical interest today, as we are facing the issue of climate change and global warming and all related issues. So he has, to his credit, uh, five completed PhD, 12 ongoings, and a lot many BTech and MTech students with him. So we feel privileged, sir, to have you with us today. And on behalf of this State Pollution Control Board, our chairman, and all of us, I welcome you to this session and would request you to present your talk, sir.
Thank you, Chairman Sir, and all the members of the Bihar Pollution Control Board. It is really, I feel it's an honor for me to make this presentation. As in the very beginning, you told that there should be a constant academic exchange between industry, the regulatory authorities, and the academics. And probably this is one such attempt which Bihar Pollution Control Board has started, and this is going to be the 22nd lecture. I'm so happy to hear that this initiative has been taken and wish this to continue for longer times ahead. Thank you very much. I will give this presentation. I will complete my presentation around 45 minutes. I will take for the presentations. I will first briefly talk a little bit about why we are talking of carbon capture, utilization, and storage. Why at the very first we want it, and then I will go to different scenarios, and I will try to put them as concise manner as possible. Okay, let me see why these slides not moving. Just seeing that my slide is not moving. Is my slide moving? No,
No, sir. No, sir.
No.
no, yeah. Let me find out what happened.
I think, sir, you will have to upload it.
You should again.
Upload.
I have shared the screens. Okay.
Sir, you sign out, then you again you upload the slides.
Okay,
You
okay.
close the slides, then you again
Right.
reload it.
Yeah, it is now moving. Can you see?
Yes, sir.
Now it is moving.
It is moving now. Yes,
Yeah.
sir. Fine,
Perfect. Okay.
Perfect.
Okay. So all of us are aware that climate change is there in real. It is in front of us. It is being manifested in different types of natural anomalies, which could be in terms of excess heat, excess rain, excess snowfall, or loss of biodiversity. And each of them has its socio-economic consequence across the globe. We are experiencing it. Here I put a small snapshot of last couple of years. There are enough evidence to tell the skeptics who think still climate change is not real. Here are a few evidences which clearly tells the climate change is real. We see Arctic sea ice is melting, ocean temperature is increasing, air temperature on the surface increasing, sea level rising. All those evidences that I have put in this slide briefly tells about these are 6-7 practical things which are measurable and which are being measured by the scientists, and the trend of that clearly indicates that there is some change in the climate and it is real. Few examples I give here. This is a picture I have taken from USGS website. You can see that in 1928, the glacier, the South Cascade Glacier was at a point which has now gone up, that is receded from its point, leaving a small water pool at that place. What it indicates is what I showed in the previous slide, that glaciers are melting, glaciers are receding. This is a danger to the perennial rivers, which are the water supply source. And India is one such country which also depends on a couple of rivers from the snow-fed rivers from the Himalayas. This is another slide to show you another glacier that in 1958, the glacier was up to an altitude of 700 mRL. So it is now receded and almost 200 meter it has gone up to 1900 meter mRL. So it shows that the glacier melting is real. And what would happen with this type of things, this long type of fluctuation? We are seeing them in the form of biodiversity loss, extreme weathers, which could be storms, floods, heating, droughts. And also there are loss of species also we are seeing. The persons who are involved in looking after the species extinction, they are very clearly detailing how the species is changing. So why is climate change is a problem? In one is the extreme weather, which we are facing. The other thing is the change is happening very fast. See, climate change or the weather pattern changes, even if the anthropogenic contribution is still not there due to the solar periodicity. The climate changes. There is a heat and cold phase in a cycle of 25 years, 30 years that happens on the earth. But our anthropogenic activity has made that perturbation a little bit faster. So this faster change of climatic pattern has become difficult for coping up of the animals or human beings who are being acclimatizing with a certain climate for quite some time, and then say abruptly see there is a change of climate. So this is the real problem. One example I have given here, say say the bears, the polar bears who hunt in the sea, the ice is now melting. So they have little place to stay. Forget about their hunting. They have no place to even stay. This is more, this climate change is happening or is being occurring very fast in the polar region. So the polar region, animals or the countries which are very close to the poles, they would experience it very fast. Of course, the tropical countries, we are also seeing the change in it, but this is happening very fast due to the melting of snow ice as well as the permafrost also. I'll talk of that also. So why we are talking most of melting of ice? There is a reason for that. Ice acts as a perfect reflecting surface. Any sunlight that falls on the earth, almost 80% of sunlight gets reflected back when it falls on that bright surface. Now, because that bright surface of the snow or ice is reducing, so therefore heat radiation or the heat reflection from the earth is decreasing. As a result, more and more water and land surfaces are available on the earth, which absorbs the heat during the daytime and radiates the heat during the night time, making the earth as well as its surrounding climate warmer. That is what we call global warming. Two examples I have given how this is a loop type of things. Say, for example, if you take snow and ice melting. So snow and ice melting takes place, you have less snow and ice. So you will have more sunlight are getting absorbed by land and sea. That is what I told. So it is taking you to warmer temperature. Warmer temperature is again bringing you to melting of snow and ice. So this loop continues. So this loop ensures that this heating and melting of ice becomes faster and faster. The other part is the permafrost, that is mostly in polar region, in the Siberian region. Again, when the temperature rises, ice melts. So below the permafrost, lot of carbon dioxide and methane are being trapped. Actually, now the talk is going on what we call gas hydrates as a source of a supplement energy to the coal, oil, or gas. So there is a talk going on that there is enough amount of carbon dioxide and methane, especially methane we need as a clean source of fuel that is being trapped in the permafrost. But because of heating, that is also melting, and methane and carbon dioxide getting released to atmosphere. Both of them are greenhouse gases. In fact, methane is almost 20 times more potent greenhouse gas than that of carbon dioxide. So the problem, as I discussed, the problem is everywhere. Tropical countries facing a lot of flood, drought, due to heat, a lot of forest fires, and also the melting of the ice. So there is problem with climate change. Here I give a slide to give you an example. What is the model prediction that if 1.5 degree temperature rise takes place, the average earth temperature rise takes about 1.5 degree centigrade, about 70% of the coral will get extinct. And if rises by 2 degrees centigrade, it's around 99% would be extinct. Right now, the scientists are talking of about 0.3 degree, 0.4 degree, or maximum 0.5 degree change of temperature. That is, they are anticipating, and we are talking of that only. And there is a projection that if we do not take appropriate control measures now, we can see a temperature rise up to 1.5 degrees centigrade. In fact, IPCC, Intergovernmental Panel on Climatic Change, they are forecasting different type of situations. So they have projected 2 temperature situations. So same thing, if you see the species loss, if the temperature rises 1.5 degree or 2 degree, you will see there would be about 20% loss of species. Drought and rise in the sea level. See, rise in the sea level is again a real problem. Few of the Nordic countries, especially Norway, Sweden, Netherlands, they have already witnessing this. That with those countries, they are lot of their land surfaces almost at par with sea level. In fact, some of the land surfaces are below the sea level, which are being, the sea water is being kept away by making different type of arrangements. So when in those countries sea level rises, they will be the first victim. It is also being projected that if 1.5 to 2 degree rises happens, then most of the coastal areas of India will also get submerged. So climate change affects us everywhere, whether winter flooding, landslide, coastal erosion. But the scientists are trying to understand, but we would say we have still not understood the entire process. So I just write here that this landslide event, why it is happening, probably at this stage also our understanding is very low. Similarly, say for example, hurricanes, we are a bit better understanding and we are predicting them, but still we need to have more understanding of this and need to link it with the climate change. So this was the first part of my presentation to let you know what is the problem of climate change, and if the temperature rises, what would happen. Now, why this is happening? This is happening because of the greenhouse gases presence in the atmosphere. What is greenhouse gas? The gases which do not allow the radiated heat from the earth to escape to the surface. Sunlight, when sun rays falls on earth during the daytime, it comes as a short wavelength radiation. And this short wavelength radiation, these gases allow those short wavelength radiation to pass through them and fall on the earth. When they get radiated in the night, they change to long wave radiations. And these gases have typical property that they do not allow long wave radiations to escape to the atmosphere. So therefore, there is a buildup of temperature due to this radiated heat during the night or afternoon or cloudy times. So when there is a radiation of heat from the earth taking place, and this is making the earth warm. So these gases are called greenhouse gases, similar to greenhouse effect. You know, in cold countries, people plant the trees in the glasses because the glass allows the heat to come in but doesn't allow heat to go out. So which are the greenhouse gases? Carbon dioxide, methane, nitrous oxide. There are F gases like chlorofluorocarbons and many other F gases are there. But out of all of them, if you see with carbon dioxide, we are more concerned. CO2, we are more concerned because as you can see these graphics, almost 70% of the greenhouse gases are consisting of carbon dioxide. I told you earlier that, yes, I told that methane has the more global warming potential than carbon dioxide. Yet, we are more worried about carbon dioxide simply because the amount of carbon dioxide being released by the anthropogenic activities are huge in comparisons to methane. Almost 40 billion metric ton of CO2 across the globe is being now released to the atmosphere. So, what will the future climate look like? Global warming due to greenhouse gases will continue for so many years because see, these gases also have a life in the atmosphere. If you stop emitting these gases, it doesn't mean that all gases disappear from the atmosphere. Different gases have different residence time in the atmosphere. So even if you switch off all the CO2 producing industries now, still you are going to face the global warming for couple of years. So how much warming really happens depends on what business or how we are burning the fuel, because burning fuel, especially fossil fuels, are the main source of carbon dioxide. If you take a summary look of where from these greenhouse gases coming, you will see that about 50 to 60% of the greenhouse gases or CO2 is coming from fossil fuel and cement industries. Then there are few from forestry and other land use. Forestry and other land use means when you clean out the forest, see, trees are the natural sink of CO2. The more the trees, they need more photosynthesis, and you know that for the photosynthesis, CO2 is required. So a lot of CO2 are being taken up by the plants. So the deforestation means indirectly you are adding CO2 to the atmosphere. And land use pattern. Land use is the more you till the soil, the more you keep the soil barren, the more CO2 that is trapped in the soil also get released. So we are changing those things. Then methane usually comes from agricultural and Western energy. Then N2O and F gases, they are very minor. So what it shows that almost 70 to 80% of the CO2 is coming from land use, land pattern change, and fossil fuel and different industries. Cement industries is a major industry. This slide I was just talking of that if CO2 has a global warming potential of 1, methane is about say 80 times, nitrous oxide is about 270 times in a 20-year horizon, and then CF4 is about 50,000 or 5,000 times more potent greenhouse gases. But as I told that because these gases quantity in the atmosphere is very less, so therefore carbon, so when we talk of greenhouse gases, we mostly talk of control of carbon dioxide. This gives an idea about how the carbon dioxide emission is increasing over the years. So in 1950, it was about 10 billion metric tons. So now you see it has gone up to 50 billion metric tons. You can see that COVID has taught us, the environmental scientists, a lot of lesson that there are still scope to do the remedy to protect our earth. One such example you can see in 2020 graph. You see after 29, there was a dip in the CO2 emission graph, and again it picked up in 2021. So that was the COVID year when the traffic was less, industrial activity was less, and therefore CO2 emission went down. So there is a scope, or there is always a scope that we can try with different options to control CO2 emissions. These two pictures to give an idea as to how the temperature is rising in parallel with CO2 concentration. The first graph shows that if you consider the global average temperature about 20 to 25 degrees centigrade, that is around 57 degrees Fahrenheit, you will see that almost after 1940, the red bars indicate the temperature is going up and up and up, and simultaneously CO2 is also going up. And that is in the next graph, it is shown in terms of zero. If you take zero as the base, then you would see that until 1950, there was a fluctuation of temperature, and most of the time the global temperature or the yearly temperature was lower than the average global temperature. But since 1940-50, things are going up and up. Lot of conferences, lot of meetings happening, you know, Kyoto Protocol, Paris Agreement, Copenhagen Accord, so many COP meetings are happening. But you see, we are planning, but still we have not seen any visible symptom of temperature going down. So this is what tells us that it is now time to act. We have a lot of debate and we have a lot of protocols. Although there are in few protocols, there are some disagreement in consensus, but almost all countries agree that they need to do to control the climate. This is, I have taken a website from National Ocean and Acidification website of USA. You can see that CO2 is going up and up. 2022 March, it was 418 ppm in atmosphere, 425 next year, and this year in March 2024, the CO2 level is about 425. 285 ppm was about the CO2 level that was pre-industrial time, that is what is being modeled. There is a group which is called 350.org. So that is, if you visit the 350.org, they probably postulate that if we bring down the present CO2 level from 425 to 350 ppm even, then this accelerated heating will stop. So therefore, in this graph, you could see there is a 350 line highlighted, that it is almost impossible now to go back to pre-industrial period of 285 ppm. Scientists more or less agree that if we can bring down CO2 to about 350 ppm, then this climate change could be stopped. This is a famous curve which is called killing curve, that is concentration of CO2 over the years. This was being devised by Charles David Killing. So this shows the yearly fluctuation, but the whole picture to say is that it is going up and up and up, and the projection is right now you are about 420 ppm. It is almost going to touch around 480 ppm level of CO2 in the next 50 years. And what are the activities that is causing this greenhouse emission? We just discussed in the other slide. Mainly three things: burning fossil fuels, whether you burn in industry, whether you burn in your vehicle, or whether you burn in your domestic use. Burning of fossil fuels is the prime reason, contributes about 60% of the CO2 emission. Then deforestation, that is land use pattern change. Soil erosion from emissions from the soil and deforestation process, and also reduction of biodiversity. That is, as the biodiversity reduces, CO2 uptake capacity of the biosphere also decreases. So these are the three main reasons. The prominent two reasons are burning of fossil fuels and deforestation. So this is this was the second part. What I wanted to deal with, what were the reasons for this global warming or climate change. Now, how to deal with this? Now, to deal with this, the first thing is that we stop emission. If we stop emission, then everything is solved. But that is not possible, because in our day-to-day life, for our livelihood, food, clothes, shelter, for everything, you need to burn some fuel in the manufacturing process. So how efficient that burning process, people are working on that, how to optimize the burning process so that less emission would be there. But burning of fossil fuel is going to continue for a few more years. Renewable energies are gradually supplementing. Solar energy, almost 5 to 10% supplement we are getting from solar energy. But there are other forms of energy like wind energy, wave energy, and geothermal energy. In that, there are very less work is going on. Wind energy also, after solar energy, wind energy is also coming up in a big way. But they at present constitute maybe about 2 to 5% maximum across the globe. So what are the alternatives we have? That if we have to burn the fuel, we cannot replace the present fuel with the renewable energy. So the other way left with us is that then the CO2 that is being emitted from the process to the atmosphere, can we stop them? So how do we stop them? Probably we collect those CO2 from the place where it is getting emitted to the atmosphere. We collect them, we prevent them from going into the atmosphere. That is what is called carbon capture. I want to capture the carbon that is going to the atmosphere. Now, after capture, what should I do? I have two options left with this. Either I can use them for some other uses, that CO2 will be the raw material for some other productive process or productive product. Or if it is not that way, then I should be able to store it somewhere so that it doesn't go to the atmosphere. So that is where it comes the word which is called CCUS, carbon capture, utilization, and storage. Storage comes only after we fail to do the utilization. And the enormous quantity of CO2 that we are emitting now, it is almost now impossible to use all the CO2 that is being emitted. So storage is being considered as a very active, viable alternative to this. So there are a group of people across the globe. Some are working on capture technology, because capturing CO2 is also, there are different intricacies associated with this. How to capture it? You have to increase its density. You have to transport it from the place of origin to the industry where you want to utilize, or the place of where you want to store it. So this is what is the entire these 4-stage process. That is, you capture the CO2 from an activity, you transport it to a destination where it will either be utilized or it will be stored. So this entire 4-stage process is what is called carbon capture, utilization, and storage. People are now also talking of direct air capture, that is also directly capturing the CO2 from the air. But that has and anybody is telling something?
No, sir. Please carry on, sir.
Okay.
No one.
So the direct air capture is the people talking of how to capture CO2 from air, but that is the economic viability still not have been possible, because the CO2 percentage in the air is very less, 0.03% that is you get in air. But to capture the CO2 from an industry, you need almost 20 to 30% by volume of CO2 should be in your flue gas. So now what we are talking of carbon capture is mostly from the industrial emissions. Now, this is a broad picture to tell you the 4 stages that is involved in the carbon capture and storage. You selectively remove CO2 from the smokestacks. Why selectively? Because from the smokestack, including CO2, a lot of other gases also come out. So you will have to specifically capture CO2 out of that. Then you have to compress and transport it, because if you want to transport it as a gas, it will require a lot of volume. It will be a lot of volume. Not only that, gases will have to be transported at a very high pressure also. So the usual process is compress it to a supercritical fluid and then transport it. Then utilization, what type of utilization you do, or you store it. We'll talk of storage options just after a couple of slides. First, let us talk of a capture scenario. Usually, there are 3 standard processes of capturing CO2 from the industrial process. One is post-combustion. That is, once the burning process over, you separate CO2 from the flue gas, compress it, and transport it. The second one is pre-combustion. That is, directly you convert the raw material into gasified form and then take H2 and CO2 out of that, separate it out H2 and compress CO2 and transport. The other one is oxy-fuel, where you provide more and more oxygen to the process and generate CO2 and you capture it. These are the 3 traditional processes. And in these 3 processes, there are absorption mechanism, distillation mechanism, use of membrane filters and chemical looping. I would not go into details of this, but I will briefly tell what it means. Absorption means you absorb the CO2 in a suitable medium. And right now, the most prominent chemical that has come out for the absorption of this is called amines, monoethyl amines, diethyl amines. In fact, across the globe, all the carbon capture technologies are using different forms of amines or amines mixed with piperazine. That is also a family of amines. So a different combination of amines are being used to absorb. For adsorption, activated carbon and zeolites are being used. There are membranes being used also to separate CO2. And there are microbial processes, algae and other processes. People are working on this. This algal process is going a little bit slow. Out of these four processes, the first process, absorption process, is really has been matured in countries like Norway, Netherlands, US, who are pioneer in this carbon capture technologies. Some simple descriptions I have given, that in absorption you use an amine-based solvent which traps CO2 chemically or physically. Then you use solid adsorbents, just like packed bed filters to absorb CO2. Then there are cryogenic process, solid looping process, different processes through which people are now working to capture CO2. Once you capture the CO2, then maybe the place of where you want to use or store may not be close to your place. So you need to transport it. So you have to transport, whether you transport through ship, railway, road, or pipeline. Pipeline appears to be the best option. Most of the countries actually going for pipeline transport. In India, we have not yet put much stress on storage and transport. Now, the Indian research is mostly working on capture technology and to some extent transport technology. Storage technology, storage not technology. India is now investigating what are the likely places where this could be stored. So storage and transportation is not being on much emphasis in India. Now, this is a schematic which shows you exactly what are the different options available for to store the CO2, that supercritical CO2 that you get. There are options like depleted oil and gas reservoirs. This is there in practice for by the oil companies since last 20-30 years. You know that oil and gas in an aquifer, they remain under tremendous pressure. Once you open up the well, due to inherent pressure, the gases come up, then you pump the fuel out. After some time, the pressure of the well goes down. So to get remaining gas or remaining oil, you need to pressurize that basin. And that pressurization is being done by injecting CO2 at a high pressure. That is what is called depleted oil and gas reservoir. So this is also called EOR, enhanced oil recovery, that you get enhanced oil recovery by injecting CO2. So this is a form of storing CO2 and getting your energy source out. Use of CO2 enhanced oil recovery, I just told you. Then deep saline reservoirs. See, we get water from the aquifers. Besides sweet water aquifers, which provides us drinking water, there are so many saline aquifers are available below the earth. So those are the potential places where CO2 is being injected. Deep unminable coal seams. Coal contains methane, and methane is an explosive gas for people who are working in mines. CO2 at a higher pressure, if injected into that coal bed, CH4 gets escaped. So you get CH4 as a source of energy. CH4 coming out means your mining is safe, and at the same time you are storing CO2 in the pore spaces of the coal. So that is what is called deep unminable coal seam, because if you use the coal seam which you are going to mining 20-30 years down the time, then there is no point. So deep seams which at present technology looks like not mineable, you can go for that. So these are different options that in a geological storage you can do. The prominent one at present is being worked is depleted oil and gas reserve, depleted oil gas reservoirs, then unminable coal seams and saline aquifers. This is what I told in the last one. And then people talk of ocean storage. Ocean storage means not only storing those in the bed of the ocean, but throwing the CO2 as a fluid into the water of the ocean water, at least at a depth of about 1 kilometer below the surface. So because it is denser than water, it remains there. Lot of the word that is being used is called CO2 lake. That is within the marine atmosphere. you are creating an artificial lake, water among the water, but this is the CO2 critical fluid. But this technology hasn't really gone on because of this technology tells that you inject the CO2 at least 0.8 kilometer below the surface in the form of a supercritical fluid, and as it goes down and down under higher pressure, its volume decreases. So because its density increases, so you will have more space to store them in the ocean. But this has not really gone up, or not even a single viable project. People have worked on this, sensing that it will be harmful for the marine ecosystem due to some reason, due to oceanic current or some other things. If this artificial CO2 lake melts down and CO2 level goes up, then the reacting with water, it will for carbonic acid and the seawater become acidic, which will not allow the marine life to survive. So this ocean storage option really haven't been worked anywhere. This is one of the best technology, which is called mineral storage. So here what we tell, this is the best in the sense that here CO2 loses its identity, it loses its forms. The idea is that mostly alkaline earth materials like calcium, magnesium, calcium oxide, magnesium oxides, if you react CO2 gas with them and form them as calcium carbonate and magnesium carbonate, which is a stable product, it's a stable product. So CO2 will never come up from there. Like the geological storage, where you are putting the CO2 below 2 kilometers of the earth, maybe due to any earthquake activities, any other activity, there is chance of leakage. There is one example in 1996, there was a project which is called Sleipner project, which was off the coast of Norway. So they had injected CO2 in the Sleipner area below the seabed. After 10 years, due to some activity, the leakage started from there. So that was famously known as Sleipner leakage. So putting CO2 in the geological bed is an option, but it has a caveat that in extreme cases, it may come out of the that reservoir. But this mineral storage is good in the sense that CO2 loses its identity, gets transformed to another product. People are now actively working on this in India. Quite a few labs working on this. Not a single commercial project has started now. Then besides this, people are also talking of different type of geoengineering, that is the utilization part of CO2, which people are talking of artificial trees, that is extract CO2 from the air and burying it in the ground. That just like the tree does photosynthesis and takes up CO2, similarly, you do the engineering structures which will trap CO2 from the atmosphere. Biochars, ocean fertilization. Say cloud seeding is another option where we spray seawater into the clouds to precipitate the rain. So people are also talking of different type of geoengineering to take care of CO2 in the atmosphere. So that was CCS, I talked most of storage, and CCU, that is carbon capture and utilization, talks about recycling or utilizing this CO2 instead of storing them permanently. This CO2 could be used as fuels or in some chemicals, or maybe CO2 pellets mixing with something else. You can make pellets to be used. So people are talking of CCU, carbon. In fact, CCU is the best option. If you can use it as a different product, that is the best way. You don't have to look for storage place. So here are the options. There are a number of options that this captured CO2 could be used, starting from food to biological conversion, then different type of extracts, mineralization, we just talked of that. then methanol, ethanol, all the products we can. Fertilizers in India also the plants have come up which are using CO2 in the fertilizers and producing sodas. So different options are also there are available that the captured CO2 could be utilized. Now I come to the last section of what is the global scenario that we talked about carbon capture, utilization and storage. What is the global scenario? The first recognizable project was around 1970 in Texas. At present, there are commercial activity about 30 plus operational CCU facilities across the globe are there. Most of them are either in US or in European countries, mostly confined to Germany, Netherlands, and Norway. Norway, in fact, is one of the pioneer country in this carbon capture as well as storage technology. It is anticipated that with the present initiative, about 100 plus such projects will become lively, will be working for the CCUS around 2030. Now let us quickly come to the Indian part of what the CCUS initiatives we are taking in India. India has also in the last 5 years, a lot of activity just started. Most of them are in the piloting scale, but one or two cases are there which are also in a very commercial scale and it is being running for a long time. So few examples like Tata Steel has recently commissioned a 5 ton per day CO2 capture plant in their Jamshedpur plant. This was in the last year. I think they have only installed. JSPL is also commissioning one plant in Ongur. Dalmia Cement has also been having one MOU with Carbon Clean Solution. Internationally, there are only few commercial technology providers for carbon capture. One of the leading one is Carbon Clean Solutions. Its headquarters is in London. And this Carbon Clean Solutions, most of the technology of this Carbon Clean Solutions are being provided to Indian company by this UK-based company. In fact, I would like to inform that I'm very happy that this Carbon Clean Solution, one of the co-founder is my student who was doing his BTech project under my supervision in 2010. Is Pratik Bam, who is now one of the director of this Carbon Clean Solution. Then other companies like Vale and Simfar, they are working on piloting. This Tuticorin chemicals, I will talk more about them in later slide. They are the one of the most viable carbon capture and utilization industry, which is being running almost for the last 15 to 20 years. When this CCU and S we are even not talked of, they had purely done it for their commercial purpose, which is now TFL is one of the example in India as to how to you plan for CCUS. Then petrochemical companies, they are also coming up. ONGC and IOCL, they have a lot of MOU as to how they will capture and use in UR. NTPC in the last couple of years, NTPC in their different plants, they have started capture. As I told you, most of them are working on only capture. Once you capture, and many of them are even trying to use them, not storage. So that is a good thing that you capture the carbon and then use it, because storage part is very less investigated by the Indian researchers. I'll talk about that. So different plants of NTPC, they are working on microalgae capture. Vindhyachal plant has already commissioned 120 ton per day CO2 capture pilot project. So most of them are actually pilot project. Very few, like 20 ton per day of CO2 is nothing. It's a very small amount. So commercial scale, it has to be much higher. Coal India Limited also has been investigating for last couple of years about the carbon dioxide enhanced coal bed methane recovery, what I was talking earlier, that you inject CO2 into the coal bed and you get the methane out of it. IFCO, the fertilizer IFCO is also being have installed this carbon capture, this amine-based carbon capture technologies. Over the sea coast, also the research is going on how much sea grass and algae we can use to capture. So this is a summary. There are many, not many, there are quite a few other examples are there. I just wanted to cover a broad area of how different industries and different sectors gearing up to this challenge of carbon capture and utilization. These tothicorin alkali chemicals that I was talking of, their technology is readiness level 9. As you know, TRL1 to TRL9, there are different readiness level. 9 means it is implementable. So they have already implemented it. And what they are doing, whatever CO2 they are capturing, they are using it for the production of the sodas, that is sodium carbonate. And this chemical compound they are using for many other things like detergent industry, laundry industry. So lot of so these things they are doing for last 15 to 16 years. And I had visited that place about 1 year back with related to a CCUS project, which I'll talk briefly about towards my last slide. So they are really doing very good. So if you see what I told in general is that capture technology, many people or many industry or many research institutes are working. Utilization, some of them are working. Storage, at present only the reservoir characterization and whether that is a particular reservoir where we can store, that is what going on. No transport technology is being now thought of. So most of the processes are between TR level 4 to 8. I have just given a snapshot to tell you that if you see towards the last, that is amine capture and amine adsorption, those are the places which are in TRL 8 and 9. IGCC is another technology where actually CO2 emission is less because you do the integrated gasification combined cycle. This is an advanced technology of the power generation technology. So those are under TRL 7, TRL and TRL 9. So the storage part is challenging in the sense that you need to do the seismic study of the area. You need to understand whether there is any chance of leakage from there. And then you have to also plan how to do the transport from the process, from the plant to the storage site. So these are the challenges for which storage is going at present at a very slow pace. Technology providers I was just talking of, because any industry wants to do, they need to have the technology provider. Now, a lot of research is going on, technologies are being worked out, but still in India, there are three industries, three technology providers which are catering to the need of the industry. One is Carbon Clean, UK-based company that I told. Besides that, two startups has come up. One is called Breathe Applied Sciences and another is Novonamic Material Science Private. Both are Indian-based startups. They are also providing support to the pilot studies of different institutes as well as industries. If you look at research and development part, around 29 plus Indian universities are working on capture and utilization. About 7 IITs are principally working on this. But most of the universities are working on CO2 utilization method or methanol production, that is utilization part. A few universities are only working on CO2 storage and transport, that I told you. And probably IIT Bombay is the only academic institution at this time exploring research on CO2 transport studies. If you see the organizational support, the government as well as organized support, I can list these are the prominent institutes where things are going on. Like DST is doing funding for a lot of the Indian and international projects. IIT Bombay and JNCSR, these two places, a CCUS Center of Excellence has been opened by DST. 3 CSIR labs, that is CSMCRI, NCL and NEERI working on that. And NGRI, that is National Geophysical Research Institute in Hyderabad, they are mostly working on the storage part. This is DST has established two national center of excellence, one in IIT Bombay and one is Jain CSR Bangalore. The Bombay part looks capture, storage and utilization, and Bangalore Institute mostly works on carbon capture and conversion process. These are the two. There is a talk that another one or two institutes of this national importance will shortly be opened. If you look at government initiatives, government initiative has also moved on with time. 2007, DST set up the Indian CO2 Sequestration Applied Research Center. Then 2008, National Action Plan on Climate Change, where again CO2 storage was talked of. And this under Mission Innovation MI, there are a lot of activities going on. One of them is what is called ACT, Accelerating CCUS Technologies, how fast we can do the technology. So now this ACT is led by Norway. Research Council of Norway is the lead or the technology assessor of this ACT technology. Right now, Act 4 is going on. Act 1 and 2, we are only for the European countries. In Act 3, India wanted to be a part of that, and India entered to Act 3. In Act 3, which was decided in 2021, Indian-based consortium got two projects. One is called SCOPE, that is on capture part, and another is called SARP, which is the storage part. So storage part is led by IIT Bombay, and the capture part is jointly led by IIT Kharagpur, our research group, and Guru Govinda Singh Indraprastha University from New Delhi. So we are right now a part of Act 3. We are almost 2.5 years. We have gone through, another 1 year we will go. So now Act 4, there are about 156 proposals were submitted. We just evaluated them a few days back. Hopefully after second screening, we will have around 8 to 10 projects. So these are the projects where there is a consortium like Act 3, where IIT Kharagpur is a partner. There are about 23 partners from 6 countries. So there is an exchange of technology between Norway, India, and other parts. So the benefit of India is to learn those technologies and bring to India. So this is in summary that in India, the CCUS projects are mostly in pilot or demonstrate stage. Large-scale execution of CCL projects is required. For that, legislations are coming up. Finance is required because this technology is very costly. Capture technology is very costly. So we not only need technological support, but we also need financial support. So if I can put 1 or 2 slides to tell how the government can play a critical role, some of them may be supportive, some of may be a type of punitive that you impose tax on more CO2 producers or more CO4 producers, so that they change from the polluted source to a cleaner source. So that is what I have put. Strictly regulate CO2, CH4, put a price on carbon emission by putting some form of tax, use a cap and trade system for CO2 and CH4, phase out government subsidies for industries which are using more and more fossil fuels. Then, of course, there are a few common things like more and more research and development you have to work out. And we need to have international agreement to have more countries which are already some sort of expertise they have. We should get them for the technology to be adopted. This is where I think India now working on. In summary, India has started accelerated working on this in last couple of years. Most of the works are concentrated on capture and utilization. Transport and storage has yet to be started. A lot of international collaborations has happened, and this needs to have more. This should happen more and more funding should come to this. Thank you very much. This is where I complete my presentation. Thank you very much for all of you for your
Thank you, sir. Let us give a big hand to Professor Patra for his enlightening and very comprehensive speech that not only dwelled with the basics of the climate change and global warming, rather the different aspects of carbon capture, its utilizations, the things involved in it, and of course, very good and doable suggestions and recommendations for combating this climate change and reduction in CO2 emission. Thank you once again, sir. And now the floor is open for discussion. I would invite the participants who are with us offline as well as online. If they have any queries, suggestions, or anything to ask, you are most welcome. Please.
So just out of curiosity, how much area it would occupy? I mean, the carbon capture unit. A typical, an average 100 tons per day capacity of unit. How much area it would occupy, sir? It would require to establish a unit. Any idea, sir?
To store.
No, sir. To install the plant.
Okay, capturing plant.
For the carbon capturing plant.
A capturing plant, I don't have any idea technically, but what I have visited the plant from Tuticorin plant, what I saw, it really doesn't need much area. Actually, this is just another plant side by side of your flue gas plant, where you divert the flue gas through the capture column, that amine-based column. So, so in a big power plant, you don't need much area actually, what I have seen. But I cannot just tell what is the number.
So my next question is that invariably, wherever the carbon dioxide is captured, I think that's stored in the liquid form. Is it so, sir?
Oh,
Wherever
yes.
captured, always stored in liquid.
You capture CO2, it has to be stored in a, say, a liquid form or fluid form, and even transport has to be done in this fluid form only. That is what is called semi-critical fluid, that you won't allow the fluid to become gas on the way. So the best way is to keep it in a fluid form. Yes.
Thank you, sir.
Sir, sir, Patra sir, namaskar, Professor sir, Dipankar. Sir, ये CO2 monitoring, emission in monitoring emission, CO2 is not being considered as a parameter in Indian industries. Is it not required to monitor this system in emissions?
In terms as a pollutant, right?
Pollutant. As a climate change pollutant, not a pollutant. As climate change pollutant, is it not required to install CO2 monitors in all emission systems, sir?
What is your question? I did not get.
But actually, the emission.
Yes, CO2 is not a pollutant because it doesn't do any direct harm to our health. Yes,
Exactly.
yes,
But
it's
it's
not a
climate
pollutant.
change pollutant. But it is nowadays a climate change pollutant. So is
Yes.
it not the right time to monitor, measure the CO2 emissions from all industrial sources, particularly the power plants, thermal power plants, more
Yes.
specifically?
I agree. I really agree with you that from our national ambient air quality standard or industry specific standards are based on the health implications.
Yes.
But now CO2 becoming even a greater implication for not only our health but the entire globe. It is high time that now CO2 be included as a parameter to be measured, not as a pollutant from the point of view of health, but of the health of the earth. Yes, I agree. I agree.
So, can you organize a seminar in this effect with the Central Pollution Control Board, Ministry of Environment and Forest, and people like you, so that we can put this pressure to have a one standard? Let it not be health standard, but the environmental standard.
This is
I-
required. This is one
I-
of the things.
Yeah, I really welcome. I really welcome your suggestion. Probably it is the time the pollution board and the academics and they sit and think how from the regulatory point of view also can be worked up so that control of CO2 emission can be done. I welcome your suggestion. Yes.
And another thing, sir, the Professor Gupta is also one of my good friend and yours too. I came to know that day I was talking to him, and when I referred about you, well, he is also a very good friend of mine. So thank you so much, sir. Thank you so much, sir.
Thank you. It is really my pleasure to interact with you. Thank you.
Thank you, sir. What I believe that our national ambient air quality standards are based concentration based. So with regard to this CO2 emission, they are not considered as a pollutant as such. So of course they are contributing to the climate change. Of course, it is not a climate. You can say a factor for climate change, a thing for climate change, but not as a pollutant because so it is just a little different from a regular pollutant that we are seeing in terms of other gases like sulfur dioxide and all. So, but hopefully, of course, the quantity is important. How much CO2 is being
or decreasing?
yes.
For
How much quantity is being
fuel?
emitted? So emission
Application
from
of clean fuel and what is the reduction that is also important.
so from the emission point of view, I do agree it is very important to consider quantify the emission coming out from a chimney or whatever the other. So, sir, I have, I think to ask you, just you have very rightly said that storage is little difficult, so it is better to have utilization to utilize it in various operations. So even going for utilization, does not it will require even a temporary storage? And if so, how to tackle with that situation?
And actually, those who are going for utilization,
Right.
that is almost a concurrent process. Usually, they don't need to have store or a very little storage space they require. They should plan in such a way that whatever CO2 is coming up, they are concurrently used. But your question I cannot answer as to how much storage space. For example, who is preparing methanol, as to how much CO2 they need to preserve for how many days. I really don't have ideas. I don't have really.
Thank you, sir. Thank you.
I had just one query because I visit thermal power plants for air quality study. So it just struck to my mind that quite a few industries told me that now it is almost FGD. That is FGD technology is almost going to become mandatory in many of the power plants. But Indian coals are very less in sulfur content, except northeast coals. The sulfur content of Indian coal is even less than 0.5%. So the amount they are investing in FGD, if such type of amount they can invest in capture technology, to me it appears, I'm not telling that FGD is not required, but FGD is required, but simultaneously some fund or some sort of pressure should be built up from the regulatory authorities about this capture. Of course, there is a problem because technology is not available now. So maybe the pollution control board can have a look as to what is the best optimum solution out of it.
Even
Uh,
sir,
it needs to be
NTPC,
exact. Yes, already NTPC is in the field in various locations as you described in your presentation. They can take the lead and they can also analyze cost, do the cost benefit analysis, including the environmental health, and this can be taken up.
Yes, yes,
I
yes.
think NTPC can do it because they are international figure nowadays. They can do help us in this.
Yes, I agree. Yes.
Yes, thanks.
hello sir.
Hello.
My question is, sir, you have talked about ocean fertilization. So, sir, India, as you know, India has vast majority of coastline. How can we utilize our coastline to store some carbon in our ocean?
ocean fertilization, as I told you, is not much work, but ocean fertilization is an option because carbon acts as a nutrient for the underwater plants. So if CO2 could be injected in those places where the marine plants require CO2, then some of the carbon uptake will be from the CO2. So that is what really the Palk Bay in from Tamil Nadu to Odisha people are working, that sea algae and sea biomass, what is their potential to take up CO2. That is what is we call ocean fertilization.
Thank you, sir. Another question is, how do you see smog tower installed in Delhi? Are they capturing carbon also?
Pardon, are they?
Louder.
No.
That is including black carbon.
It is
It's
in
everything.
Everything.
but it's not capturing.
Yes.
Not gas specific, it is capturing everything.
Sir,
Thank you, sir. Thank you so much.
Particles, aerosols are captured.
So if no further queries are there, I would like to propose a big hand to Professor Patra again. Sir,
Thank you, sir. Thank you all for your patient hearing to me. It was a good interaction with all of you. I would love to come back to you on any other subject of my interest when time comes.
Yes, sir, one subject
thank
is
you,
pending
sir.
with you,
It's
sir.
great of you. And would like to request our respected chairman, sir, for to just throw lights on way forward.
Thank you, Professor Patra, for this enlightening lecture in this capture techniques and the storage of carbon dioxide. Because this topic was much sought after, but least understood by many of us. So the next lecture in this series, the 23rd lecture, will be by Professor Amit Garg, IIM Ahmedabad, on. We'll announce the date.
The dates yet to be decided.
We have not yet finalized. And thank you very much.
Okay then. Thank you, sir. Then I take the leave.
Just sir, a few words of thanks from our member secretary, sir.
Sir has to go, sir, there is a meeting.
Okay. So, I won't take much time, sir. Sir, we are glad to have you for delivering this wonderful lecture. It was very informative, sir. Many of the engineering techniques used for carbon capture were unknown to us hitherto. So we have learned a lot from your lecture. We are looking forward to have a continuous interaction with you, sir. And also, on this very day, I would like to inform you and request you once again for another lecture for which we can have a discussion separately, sir, as per your convenience. So, and regarding FGD, sir, Ministry of Environment, Forest and Climate Change has fixed different timelines for different categories of thermal power stations. Like they have classified the thermal power plants into class A, B, C, depending on some few factors. So even for FGD, they are taking a lot of time. I'm not sure whether even by 2026 they would be able to install FGD in all the thermal power plants. And also, as per the nationally determined contributions, by 2030, the government aims to generate about 50% of total energy by renewable energy. And also, going by the NTPC's very own policy, by 2047, if I am right, they will completely convert to, they will become carbon neutral. So these are all some of the very important policy decisions, and they are. It seems they are moving towards the implementing those decisions, sir. Things will be decided as per the technological advancements, as you have mentioned, and the entrepreneur startups have two startups have come up in India, as you have mentioned, sir. I think things will be good in near future for India. Thank you so much, sir. Thank you for delivering this wonderful lecture once again. Thank you so much.
Thank you so much, sir.
Thank you to all of you. Thank you. Okay, bye for now.
Bye.
Thank you, sir.